We want to solve this problem, and the problem states that consider a message signal having a maximum amplitude of 10 millivolts that is double-side modulated or double-sideband modulated before transmission. If an imperfect local oscillator at the receiver introduces a constant phase error of this magnitude, that is pi over 8 radians, then the question is find the percentage change in magnitude and phase of the received message. So we want to find how much change, percentage change in magnitude we realize in magnitude and in phase. So the first thing we do is just remember the basic building block of double sideband modulation, whereby we are now considering the receiver. So the receiver will get a double-side modulated signal x DSB of t, which is multiplied with a local oscillator that is having the same carrier frequency as that of the transmitted message, and they are multiplied at this point, and what we get is a message signal that we refer to as dt, and the dt normally has a high frequency component such that when it goes through a low pass filter, it is removed and you are only left with the desired message signal y of t. So having said that, what we just need to notice is that we are told that this local oscillator introduces a constant phase error phi, which is equivalent to pi over 8. So I've just made this correction, which was indicating 0 pi over 6, so it's supposed to be pi over 8. So we are saying that the phase that is introduced, which remember that this is our phase. So we are going to consider that our input message is equivalent to mt cos omega ct, and this is something we have done in the past, such that you know that d of t, if this is our input message, will be the multiplication of the input message with that of the carrier, with that of a local carrier. So this is what we are simply getting at this stage. So we say dt is equals to the input and the local carrier frequency component. So when you do that multiplication, what that gives you, now what we are saying is that the local carrier has phi. So as I mentioned, has a phi whose which has a constant phase error of pi over 8. So when we do this multiplication, so just to be clear, just to be clear here, is that we are saying that this is the local carrier that is having, that is the one that is introducing the phase constant phase error of pi over 8, and therefore this is where we have the constant phase error. So if we do this multiplication, we are actually employing the known trigonometric identity that we have cos A, cos B. This is always given by 1 over 2 cos A plus, not 2. This is normally equivalent to cos A plus B plus cos A minus B that to be the case, and therefore if we let A to be equals to omega c of t and B is equals to omega c of t plus phi, then A plus B will be equals to 2 omega C of t plus phi, whereas A minus B will be equivalent to, if I want to make them, doesn't really matter, will be equals to phi, because this might be minus phi if we just that minus these two, but we know cos of minus phi and cos of phi are the same. Therefore, even if we write phi, that's okay. So this is how we get this figure. We have cos phi and 2 omega c t plus phi. This is the plus version. So once we do that, then we can open up the bracket. And when you open up the bracket, we get this term that is coming from this one, and the other term 1 over 2 mt cos omega 2c cos 2 omega ct plus phi. And therefore, then when we pass this signal through the low pass filter, just as we have indicated, we have said that now this dt has these two terms. So, and this is a low pass filter. It actually cuts off the high frequency component. You can see this has a double frequency. So this is going to be cut off. Therefore, you are going to be left with 1 over 2 mt cos omega cos phi. This is the one that has the phase error introduced. Of course, if the phase error, if the phase of error is equal to 0, then cos of 0 will be equals to 1, therefore will not be effect on the message. But if there is a phase error that is bigger than 0, then it is going to introduce some significant error right there. So what we are saying here is that the second term is cut off by the low pass filter. That is what I have just explained. This term gets dropped. This term gets dropped. Dropped by LPF or low pass filter, and therefore we are left with y of t being equals to this. So what we are asking, the question is asking is, find the percentage change in magnitude, first and foremost in magnitude. So how we do that is, we know that if there was no phase error, then this would have been 0, therefore our message would have been 1, or would have been multiplied by cos 0, which is 1. But if the presence of this phase error, that means there is introduction of this value, which is cos of pi over 8, which is equivalent to 0.9239. Therefore, the change will actually be difference between 1 and this one. So this 1 minus 0.939 divided by 1 times 100, and it gives us a percentage change is actually 7.61. And the other question is asking what is the percentage change in phase of the received message. What we can see is there is no effect on the phase, because purely this is not affected by the phase error, constant phase error. What is affected is by the magnitude, because clearly this is not a function of time, therefore it will not affect our message signal, and therefore we simply say there is no effect, there is no change in phase of the received message. That concludes our solution to that problem.